Hi, in this video, we're going to continue with the theory for number theory, and we are going to start with a discussion about divisors. So, divisors of a number n. Here, n is a positive integer, and basically, if you can represent n in terms of its prime factors like this, here p1, p2, pk are all prime factors, and this is the prime factorization of n, where e1, e2, ek are the exponents of the respective prime factors. Then the number of divisors of n is simple. It's a simple argument. It will be e1 plus 1 multiplied by e2 plus 1 and so on till ek plus 1. This will give us the total number of divisors of this. It's a combinatorial argument. Whenever you construct a divisor, you have to put some power for all of these prime factors. And the powers can be anything from 0 to E1, right? So there are E1 plus 1 choices for powers of P1, and similarly, E2 plus 1 choices for powers of P2. So therefore, the number of ways in which you could construct a divisor would be by multiplication rule, product of these many choices, right? So this will come out to be E1 plus 1 multiplied by E2 plus 1 and so on. Now, suppose you want to find the sum of all of these divisors. Suppose we want S of n, which is sum of all the divisors of n. So how do we find S of n? So S of n will be simply add up all the powers here, 1 plus p1 square till p1 power e1, then multiply 1 plus p2 square, so on till p2 power e2, and so on till 1 plus pk square till pk to the power ek, right? So this entire product will give us the sum of all the divisors. Now you can simplify that a little bit by using the geometrical progression formula. So you can say S of n will be, I'll just write the expression first. It was p1 square till p1 e1 and 1 plus p2 square till p2 e2 and so on till 1 plus pk till pk power ek. So in each of these factors, you can apply the GP formula and you'll get this p1 power e1 plus 1 minus 1 by p1 minus 1 multiplied by p2 power e2 plus 1 minus 1 by p2 minus 1 and so on till pk power ek plus 1 minus 1 by pk minus 1. So this is the expression for S of n, right? Another way to write it in a symbolic way would be, what is d of n? D of n was the number of divisors of n, and d of n can be written as summation of all the numbers such that d divides n. So this summation is basically only counting those numbers d which divide n, and you're adding 1 for each of them. So this will give you d of n, and S of n can be written as summation d divides n and summation of all of those d, right? So this is a nice and compact notation for S of n, right? Now, related to the sum of all the divisors is the idea of a perfect number. So we'll discuss briefly what are perfect numbers. So the numbers for which S of n is equal to 2n, right? Which implies that sum of all the divisors of n, excluding n itself, excluding n, is equal to n. So basically the sum of all the proper divisors of n should be adding up to n. In that case, that kind of a number is called a perfect number. For example, a perfect number is 6. The divisors of it are 1, 2, 3, and 6. So we will exclude this divisor because it's not a proper divisor, it's itself equal to n, right? So the proper divisors are 1, 2, 3, and 1 plus 2 plus 3 is equal to 6. Here S of n would be equal to 12 actually. So S of n is equal to 2n, that means it's a perfect number. Another perfect number is I think 28. You can check that yourself. Now there is some terminology that you should be familiar with. If S of n is greater than 2n, then the number n is called an abundant number. Called an abundant number. And if S of n is less than 2n, then n is a deficient number. Deficient number. And if S of n is equal to 2n, obviously it's a perfect number. Now there is a nice criteria for perfect numbers. This criteria was given by Euclid, which says that any number of the form 2 power k multiplied by 2 power k plus 1 minus 1 is perfect if 2 power k plus 1 minus 1 is prime. So if this part of it, this number is a prime number, 2 power k plus 1 minus 1, then the product 2 power k times 2 power k plus 1 minus 1 is perfect. So let's try to prove this criteria. So we'll do that on the next screen. We'll say since 2 power k plus 1 minus 1 is a prime, then the number n, which is equal to 2 power k times 2 power k plus 1 minus 1, is the complete prime factorization of n. Complete prime factorization of the number n, right? Because this is powers of 2, which is a prime number, and this is itself a prime. So this must be a product of prime. So it is a prime factorization of our number n. Now, if we try to take S of n for this number, according to the formula for S of n, you should realize that we have to do 1 plus 2 plus 2 power k here, and there is only one prime factor here. So that will be the sum of the divisors would be 1 plus 2 power k plus 1 minus 1, right? Because the power of this prime is 1, so you take one case where you don't include that, and the other case is itself, right? So this is the S of n according to the previous understanding of S of n, right? So this becomes 2 power k plus 1 minus 1 by 2 minus 1 multiplied by, this is what? This is 2 power k plus 1, right? So this is becoming 2 power k plus 1 minus 1 multiplied by 2 power k plus 1, which is equal to twice of 2 power k into 2 power k plus 1 minus 1. Now notice that this is our n, so we are getting S of n is equal to 2n. So since S of n is equal to 2n, the n is a perfect number. So any number of this form, if the inside part here 2 power k plus 1 minus 1 is a prime, then the number 2 power k times 2 power k plus 1 minus 1 becomes a perfect number, right? Let's look at the next item in the theory. So we'll look at Fermat's theorem. So what is this? It's a very important theorem. So what we'll say is if we take powers of some number a, powers of some number a, where a is not congruent to p, where a is not congruent to 0 mod p, right? Then the numbers a, a square, a cube, and so on cannot all be different, if you are thinking of it in terms of modulo p. We are thinking of all of these numbers a square, a cube in terms of modulo p. And we know that a and p, a does not divide p, right? So a and p have GCD equal to 1. In that case, what we can say is a square, a cube and so on, this sequence cannot all be different mod P, because there are only P possible remainders from 0 to P minus 1 when we do mod P, right? When we are looking at mod P of any number, there are only P possible remainders, 0 to P minus 1. So this infinite sequence of numbers, all taken mod P, cannot all be different, right? Some of them must be same, no? Because they will all fit into 0 or P minus 1, something in this range. They will all have remainders in this range. They will all be congruent to some numbers in this range, right? So therefore, some two of them must be the same, modulo P, right? So let's say the two powers that are the same are a power r and a power s. So we are getting a power r and a power s is same modulo P, congruent modulo P. And assume that r is greater than s without loss of generality. So then we can divide by a power s on both sides. Why can we divide? Because a is not congruent to P, so we can do the division without worrying about GCD of A and P, right? So A power R minus S is congruent to 1 mod P, right? Since P is a prime and A and P GCD is 1, therefore we can do this division. So what we realize from here is there is one power of A, R minus S, which is congruent to 1 mod P, right? That is what we realize. So what we can say from this is, if we keep taking powers of A square, A cube, and so on, there will come a time when we'll hit a T such that it is congruent to 1 mod P, right? Then after that, again, you will do AT plus 1 will be equal to AT plus 2 will be congruent to A square. And after that, you'll come to A power 2T, which will again be congruent to 1 mod P, right? And after that, you'll keep going like this. A power 2T plus 1 will be congruent to A power 2T plus 2 will be congruent to A square, and so on, right? You'll reach up to A power 3T, which will be congruent to 1 mod P. So basically, you're getting pattern here, a repetitive pattern when you keep taking powers. And here, the smallest positive integer for which this happens, A power T is equal to 1. The smallest T for which A power T is congruent to 1 mod P is called the period of A mod P. That is the period of A mod P. Why is it called the period? Because you are seeing a repetitive pattern. After that, it again gives the same remainders, right? It's again congruent to A and congruent to A square. You see the same pattern. So this is the definition of period of A mod P, right? Now, consider the set of numbers. Consider the set of numbers 1, 2, 3 till P minus 1. If we have this set of numbers, if we multiply all of them by A, we get the set A, 2A, 3A till P minus 1 times A, correct? Now, none of these are divisible by P, are divisible by P. Why? Because A and P had GCD equal to 1, right? A and P GCD was equal to 1. They had no common factors. So multiplying by A doesn't change anything. And what were we multiplying? We were multiplying 1, 2, 3 till P minus 1, which were anyway co-prime with P, right? 1, 2, P minus 1, there are no common factors with P, right? So the overall thing also has no common factors because you have simply multiplied with A to A, right? Since none of these numbers are divisible by P, this set of numbers must be the same numbers. All of them are congruent are congruent to some numbers in the set 1, 2, 3 till p minus 1. Since all these p numbers are congruent, are not divisible by p, they must be falling into one of these residue classes, right? They must be 1, 2, 3, p minus 1. They must be congruent to some of the numbers here, right? So what we can say, if we take the product here, product of these incongruent numbers, that should be equal to the product of these numbers, right? So what we can say is a times 2a times 3a times p minus 1 times a should be congruent to 1, 2, 3, p minus 1 mod p. And this gives us basically 1, 2, 3 till p minus 1 will get cancelled on both sides, because we can cancel it because all of those numbers are co-prime with p, right? So we don't have to divide by p, GCD of those numbers with p, right? So we will get eventually here a power p minus 1 actually, because you're going from 1 a power 1 here, a power 1 here, and from 1 to p minus 1. So getting a power p minus 1 is congruent to all of this gets cancelled, it is 1 mod p, right? Multiply it out and cancel all the 1, 2, 3 p minus 1 terms, you will get a power p minus 1 is 1 mod p, right? So basically, this equation a power p minus 1 is congruent to 1 mod p is valid for all primes p and for all a such that a and p are co-prime to each other. And that is your statement of Fermat's theorem, right? Now, how do we use it? We can use it in these ways. Let's calculate some things. 4 power 87 mod 17, right? So first of all, you should realize that 4 and 17 are co-prime to each other. 17 is a prime. So we know immediately 4 power 16 by Fermat's theorem should be 1 mod p, 1 mod 17, right? If 4 power 16 is 1 mod 17, this becomes 16 fives are 80. This is 4 power 16 power 5 times 4 power 7 mod 17. So technically, this is 1 into 4 power 7 mod 17. So we have to calculate now 4 power 7 mod 17, right? Now, how do we do 4 power 7 mod 17? You have to realize that 4 square is equal to 16 mod 17 congruent to, so congruent to minus 1 mod 17. So that is 4 square. So 4 power 6 will be congruent to minus 1 mod 17, because we can take cube on both sides here. So if 4 power 6 is congruent to minus 1 mod 17, 4 power 7 will be congruent to minus 4 mod 17, which is basically 13 mod 17. So that is how you apply Fermat's theorem in different problems, right? Now, one more thing that I wanted to mention is this idea. So think about it. What does Fermat's theorem imply about the period of a number, right? So period of a number mod p is at most p minus 1, right? Why? Because we have a power p minus 1 is congruent to 1 mod p for a and p to have, for co-prime a and p, this is what is coming, right? So what was period of a number? It was a power t should be congruent to 1 mod p, right? So the maximum possible period of the number could be p minus 1, right? It is possible that we get a period at a lower value than p minus 1, but this is the maximum possible number, right? The only powers which give 1 are multiples of t, right? We have seen earlier that a power t was 1, a power 2t was congruent to 1, a power 3t was congruent to 1, right? The only powers which give 1 are multiples of t. So, since a power p minus 1 is congruent to 1 mod p, that implies that p minus 1 must be a multiple of t, right? Think about it. Earlier we have seen when we defined the period of A, we saw that there is some number t for which a power t is congruent to 1, and other powers that will come are a power 2t, a power 3t. Those are the other places where you get 1 mod p, right? So the only powers which give 1 are multiples of t. And now we have by Fermat's theorem, a power p minus 1 is 1 mod p. So p minus 1 must be a multiple of t, right? Because this is a power that is giving 1 mod p. So if p minus 1 is a multiple of t, that means the period t, which was the period, is a divisor of p minus 1. Which is very nice because it gives us a strict limit on what are the possible periods, right? For example, if you look at something a power, powers of a, we are looking at powers of a square, a cube and all, but we are looking at it mod 23, right? 23 is a prime. We know that a power 22 is congruent to 1 mod 23, as long as a and 23 are co-prime, right? This is given by Fermat's theorem. Now we know that whatever is the period of this, let's say the period is t, it could be a power t was 1 mod p, it could be a power 2t was 1 mod p, right? So we know that only multiples of t can give 1 mod p. So that means 22 is a multiple of t, right? Multiple of t, or t is a divisor of 22. That means what are the possible divisors of 22? 1, 2, 11 and 22. That means we have only 4 possible values that you need to check. T can be 1, 2, 11 or 22, right? So we don't have to check the entire sequence of powers. We only have to check the divisors of p minus 1, right? So that is a very interesting idea. It will be used in problems. So keep that in mind. Now, another follow-up from there, we know now that every period, let's say that is t, will divides p minus 1, right? Now, there are interesting elements where the period t is equal to p minus 1. The period t could be smaller than p minus 1, but the interesting elements are those where period is equal to p minus 1. And then we call those elements, let's call those elements G, such that their period is p minus 1 mod p. So what that means is G, G square, G cube, G power 4, none of them will be equal to 1 mod p. It will be equal to 1 mod p only when you reach G power p minus 1, right? Correct? So for such an element, this set of powers, G, G square, G cube till G power p minus 1 is just a rearrangement of all the moduli 1, 2, 3 till p minus 1, right? Because all of these p minus 1 integers are congruent, are not going to give 1 mod p, right? So this is basically going to be different. Each of them are different from each other, right? The repetition starts after this point. So this type of element G, which has a period of p minus 1, is known as a primitive root. So G is a primitive root mod p, because the period of G is p minus 1. So we'll deal with primitive roots in more detail in future classes. But for now, in this lecture, we'll conclude this lecture. We have covered divisors, we have covered perfect numbers, we have covered period of a number, the meaning of period of a number mod p, and finally we looked at Fermat's theorem and some applications of Fermat's theorem. So that's a good point to stop here, and we'll continue with the theory in the next few classes. So I'll see you next time.